We're live, or
Hello.
not, maybe not live, but recording is on.
For us, it's live.
For us, it's live. How are you doing, Jesse?
Very well. How about yourself?
Very well, very well. So,
So,
yeah, what did you want to talk about?
yeah, what's been up? We
Oh,
haven't seen you in a couple of weeks. What's
that's
new
true.
with Neptune?
Um, we, uh, for the longest time, we were working and focusing on Triton VM and making the prover faster through all possible attack vectors and making the program or the programs for proving the correct verification of Triton VM proofs faster and smarter. Um, and that exercise, it didn't stop. We're still doing that on the back burner, but our focus has very much shifted now to writing the consensus logic for Neptune. Rules which you have to prove to have satisfied in order to initiate transactions. The rules that determine whether a transaction is valid, whether a block is valid. All those rules have to be proved, and that's why we need programs written in Triton assembler for those rules. And the reason why we couldn't do that until now is because we didn't have a fast prover until now. We didn't know what the prover would look like until it reached recursion, which was a big milestone. And now we
And
do.
so, how's the speed now of the prover?
On a rather beefy machine, we're looking at 20 kilohertz.
But I mean, in terms of the benchmarks that you were eyeing.
The benchmarks that we were eyeing, I'm not sure what you mean by that.
Well, I think I remember you saying, "Oh, if we reach this, that would be really good." I don't remember what number that was, or even what units, but I remember you mentioning something.
Right.
You
Okay.
know.
Well, in the back of my head, we are targeting blockchain parameters similar to Bitcoin's. So one block should come every 10 minutes. And that block interval, that target block interval, in the case of Neptune, is more or less divided into a proving step and a lottery step. And so we need the proving step to be significantly less than 10 minutes because otherwise the miner with the faster hardware has a consistent advantage over another miner. And that's not fair. We want the distribution of mining power to reflect the distribution of cheap energy, not fast hardware. And so in the end, that translates to recursion speeds of on the order of seconds. And no, we're not there. I think on the beefy machine that we have in our possession, we are looking at 30 seconds for one recursion. And it's not quite what we need because that benchmark is verifying the proof, verifying a single proof. But in reality, you need to verify multiple proofs inside of one program, and you need to do that several times over. So if we were to take that 30 seconds as a estimate for a small step and extrapolating across the number of steps that we might have to make, we're probably looking at 4 to 5 minutes proving time, and that's not good. So we are definitely going to have to circle back to Triton VM at some point and make it even faster. Potentially throw GPUs at it. GPUs, as I'm sure you know, unlock crazy amounts of parallelism, and the nice thing is that all that parallelism can be productively put to work in the course of producing a proof. And so we've heard from competing teams who managed to write their provers on GPUs or in GPU code that proving drops to 1 second, half a second, proving a recursive, what is it, the correct verification of a proof. And so, yeah, we'd like to get there, but we'd also like to get some progress with Neptune. And now that we finally have the target specified, we can actually write consensus programs. And in the back of our mind, we expect those consensus programs to receive an order of magnitude improvement once we circle back to Trenvia.
And so when you talk about these competing teams, what exactly are you competing on?
I'm talking about teams that are into Stark provers, basically. I'm talking about Starkware, aligned layer, polygon. I'm certainly missing a whole bunch. Risk Zero comes to mind. Uh, yeah, they are all producing provers, and they all converged on Starks as the underlying Snark technology because Starks are just the fastest. And uh, yeah, that's what I'm thinking of. They're not, as far as I know, aiming to build a privacy preserving cryptocurrency. As far as I know, they are looking to build a roll up, and some already have, on top of Ethereum. That's going to provide scalability. And so, interestingly, even though the mathematics for proof systems was originally developed chiefly for privacy. That's where we get zero knowledge from, and ZK is often used as the abbreviation of proof systems. Um, these days, proof systems are chiefly used for scalability and not privacy, and we're putting the privacy back in.
Hey, could you go into a little bit why it's a double whammy? Why does the technology lend itself to both?
Why does the technology lend itself to both? I guess that question can be answered at various levels of um, detail and philosophical profoundness. Um, I'll, I'll choose one level arbitrarily. I'd say proof systems. The thing being studied there is the discrepancy of work between the prover and the verifier, and the more interesting result means the larger the discrepancy between maybe not even work, but the required resources between the prover and the verifier. And so anything that's a resource that could be used for computing anything at all, you can turn that into a question. Can we design a proof system where the verifier does not need that resource at all, or needs only a very limited amount of that resource? And that resource could be time, and then you have scalability. That resource could be memory, in which case I'm not sure what you have. Uh, but in practice, that's
Forgetfulness.
also scalability. But that resource could also be secret information, and then you have zero knowledge.
Okay, that makes a
And
lot of sense.
one of the interesting results from the last year in theoretical computer science was another answer to that line of questions. What if the resource is quantum bits, qubits? Can you make a classical verifier running on the machine on which I'm calling you right now for a computation that requires qubits to run? And the answer is yes, assuming that certain cryptographic problems are hard, and those assumptions already underlie tons of protocols that we already use.
So that would mean that you can prove a quantum computation without a quantum computer?
Well, in order to produce the proof, you would need the quantum computer, but in order to verify it, you would not need the quantum computer.
Right. Okay. And what kind of implications would that have?
Well, it would start by killing dead in the water all the fake news about we've reached a quantum computer with 2 quadrillion qubits. Because the reason why this fake news pops up all every once in a while is because they end up measuring the number of particles involved in their supposedly quantum system, and there are tons of particles involved usually. The reason why it's a bogus number is because a physical qubit doesn't map onto the logical qubit, which is the thing that you need to do quantum computations. Usually you use many, many, many physical qubits to simulate a small number of logical qubits. And the question is how many do you need in your particular architecture? Uh, how many physical qubits do you need to simulate those logical qubits? Um, and so this this way to dominate the headlines will die dead in the water, because if you really did have a quantum computer, you would be able to prove that you have it, and everybody would be able to verify it. And I think we're gonna get there. I'm not entirely sure about the quantum computers, but the understanding that we can verify when quantum computers exist, and that this task should be easy, we're going to get there very, very soon.
And so that would manifest itself in what, a calculation that could only feasibly done by a quantum computer, and then that proof can be run by non-quantum computers.
Exactly. It would manifest itself just like a Stark proof on blockchains. You download the open source software, which you can scrutinize as you like. And that open source software requires negligible resources on your part. You can run it on the laptop on which you're calling me. And you can, by running it, you can verify beyond a shadow of a doubt claims about quantum computers having been scalable quantum computers having been successfully constructed.
Interesting. Interesting. Okay, so let's talk a bit about the consensus logic. Is that work? Is it like fairly straightforward for you guys? Like you know the more or less the rules that need to be implemented, and you're just moving through the work, or is there like, are there unknown unknowns popping up? Tell us a bit about how it is.
Um, there are two big categories here. There's consensus logic for transactions and consensus logic for blocks. And I'd say in terms of transactions, it's more or less scoped out and mapped out, and there's not that much disparity between the territory and the map. We are meeting unexpected setbacks and unexpected mismatches. It's like we have the engine ready and the transmission ready and the chassis ready, and now that we are assembling the car, we're discovering that a lot of our parts don't quite fit together, and we have to remove a little bit of material there and add a little bit of material there. Um, you know, it's the sort of thing that falls out of wrapping together threads that you were working on in parallel, but in the end you need to produce one product, and all those threads need to speak together in the same language. Um, yeah. So one such disparity, for instance, was in the course of producing the transaction logic for transaction, excuse me, consensus logic for transactions, uh, we needed a program that could verify an arbitrary number of other proofs. Um, but the recursive program that we wrote for Triton VM, it takes a proof located in a hard-coded location in memory because that's more efficient. And it's rather trivial to extend that to any known number of proofs, but if you want to extend that to an unknown number of proofs, you run into difficulties. And so we had to go back and make something that was hard coded into a dynamic solution so that you can play with the number of proofs that you end up verifying. Um, on the side of the block consensus logic, things are less mapped out, and yeah, it takes some thinking work to even know where to get started and plot out a map and a trajectory.
And so help the listeners understand that distinction between those two, between the transaction consensus logic and the block consensus logic.
Um, a transaction is just a transfer of money, and you need the initiators, what is it, the owners of the money that's being spent to sign off. You need to ensure that there is no inflation. You need to ensure that since this is a privacy preserving cryptocurrency, the outputs of a transaction and the inputs of the transaction, even when those outputs and inputs refer to the same set of coins, the output and the input, they don't look like each other at all. That's by design, because if they did look like each other, then your inputs would be linkable to your outputs and you wouldn't have meaningful anonymity. And so you need to ensure that you're actually allowed to spend these inputs. And that ties into the mutator set logic. The mutator set is the data structure that achieves this, and it requires that you prove certain facts about the mutator set. Um, Now, if you ensure those facts, and the way you ensure those facts is by proving them, then you get to broadcast a transaction. Um, but there are still other things related to transactions. For instance, you broadcasted the transaction, great. It lives in my memory pool, and I'm running a miner. And if I mine a block with that transaction, that's fine. But if someone else finds a block first, that block induces an update to the mutator set, and now your transaction is no longer valid. And so I need a way to update the proof on your transaction. So there's an update mechanism. Um, Furthermore, another supplementary technique for enabling or achieving privacy is the ability to merge transactions. So you have one transaction, I have one transaction, and we're spending different inputs, producing different outputs. They might as well be one transaction. And in fact, without interacting, we can merge them. We just have to produce a proof that the original proofs were valid. And then we can throw away the original proofs and use the new proof for the merged transaction instead. And so using that technique is how we ensure that every block only ever contains one transaction. It doesn't need to contain more transactions. It needs to contain only one transaction, which is the merger of all transactions that the miner decided to include. And when
But
you
what's the benefit of having only one transaction per block? Increase privacy.
increase privacy, because you don't know which inputs belong to which users, because when you merge transactions, you shuffle the inputs and you shuffle the outputs. And secondly, you get to throw away all the original proofs, all the original signatures, even if there were signatures. In general, we don't, but there are use cases where you might need signatures. You get to throw them away, and certainly the original proofs, you get to throw them away. And so, in the end, you only need one proof, which means that the marginal cost of one extra input or one extra output or one extra transaction is as small as possible. It's just the commitment to those inputs, just the commitments to those outputs, just the, well, I guess you don't have a commitment to a transaction, but you get the point.
So the amount of transactions you can potentially include in a block behind that one transaction is very high or unlimited.
Very high, it's still limited because you still need the commitments, still need the outputs and inputs of your transaction, but the
Is
witness
there
data is constant, is independent of the size of the transaction.
is there a throughput benefit there as well?
There is, absolutely.
Interesting. Yeah, it's like it's mind-boggling to think about this this double whammy, these implications for scalability and privacy going
Simultaneously.
yeah, yeah. Okay,
I,
very
I think
cool.
I think that's the title of the episode.
Yeah. Okay. Yeah, and like it's time to invest in GPU stock. I
Absolutely.
guess that time was a year or two ago, but
And I'm thinking the AI hype might run its course, and then the GPU stocks might drop a little, and maybe that might provide an opportunity for buying GPU stock. But remember, this is not financial advice.
yeah, yeah. So you
I'm
thought
just
about it. Cool. Anything else to mention?
uh, I wrote an article 1 week ago, last week, about how distributing mining rewards is not straightforward, or if you do it in the straightforward, naive way, then you run into problems, and some thoughts about addressing those challenges. That's worthwhile reading, I'd say.
It's on the Neptune.cash blog for those interested and those with
Exactly.
the skills to read it.
Those with the skills to read it, it's plain English, man.
Well, I saw some LaTeX math in there, so it's not definitely not pure English.
LaTeX is English. Give me a break.
Okay. Agree to disagree. All right, Alan. Good speaking with you. Good luck this
Likewise.
week, and
Thanks.
then hopefully see you next week.
Absolutely. Take care, Jesse.
Ciao,
Bye bye.
ciao.